Hello, I'm Dan Rosenkrantz. It's November 15th, 2017. I'm going to interview Dick Stearns, who won the Turing Award in 1993 with Joris Hartmanis in recognition of their seminal paper, which established the foundation for the field of computational complexity theory. To start, can you please tell us where you were born?
Yes, I was born in Caldwell, New Jersey, July 5th, 1936. The place I was born, just a few houses down from where President Grover Cleveland was born.
Can you tell us about your family background?
Yes, my father was born in Matawan, New Jersey, was brought up in Caldwell, New Jersey. His father graduated from the University of Pennsylvania. Eventually, he went into the ministry and became a minister of the First Presbyterian Church in Caldwell. He married the girl next door named Mary Jeter. My father's name was Edwin I. Stearns. My mother was born in Newark, also raised in Caldwell. Her father was born in Iowa, studied engineering at the University of Iowa, came east to work for Edison Electric Company, which eventually became GE and then RCA. He married Clara Kemper, who was born in Elizabeth, New Jersey, and lived in New York City. So I have, and my mother's name was Winifred Scales. I have a younger brother, Robert, who was retired from the Army Corps of Engineers, and a sister, Denny, who was, her last job was at Williams College, where she was director of the technology.
Growing up, when did you first become interested in mathematics and science?
Well, I should say more about my father. My father studied chemistry at Lafayette College, then got a master's degree in chemical engineering at RPI, and he went to work for American Cyanamid Company in Bound Brook, New Jersey. And he soon discovered that if he wanted to get further along, he should get a PhD. So the same year that I started kindergarten, he started studying for a PhD at Rutgers. So it's always been almost assumed that the PhD is your academic goal. My mother was a chemistry major at Swarthmore College. She was the only woman chemistry major there. And she learned a lot of mathematics, which she was able to discuss mathematics with me as I was growing up. My father was a amateur ornithologist, well known in New Jersey. And so there was a lot of exposure to science within my family. As I grew up through grammar school and middle school in North Plainfield, New Jersey. And there were several books in our home library on mathematics. One was Carleton Robbins, What is Mathematics? And it's a book by Gamow on 1, 2, 3, infinity. At some point, they also acquired a little book by Williams called The Complete Strategist, where they discussed zero-sum, two-person zero-sum games. I remember a few instances with my mother regarding mathematics. One instance, there was a fad in the school at one point where you had this they called it 16 puzzle, where you slide pieces around on a 4x4 grid. And there was a booklet that said, a list of different things you could do, like, all the numbers in sequence, or all the odd numbers, then all the even numbers. And then the last one was called impossible. And here's there are some people who claim they had gotten the impossible. The only real way of getting that is to cheat and take all the pieces out and put them back together in a different order. Well, my mother explained to me that that was impossible because you could only do even permutations. And so at that point, I learned something about permutations. Another incident that comes to mind is I was interested in probabilities and having roll dice and move pieces around a game board. And so I asked my mother about probability, and she had a book which explained the elementary principles of probability. So that was my background through middle school. Then we moved from North Plainfield to Plainfield because they wanted a little bigger house since my sister had come along. And I went to Plainfield High School. And my education there was great, particularly in mathematics. I remember the algebra teacher I had as a freshman. She always insisted that you always explain what you're doing in terms of operations. So if you were solving an equation, for example, you're supposed to say, well, now I'm subtracting something from both sides of the equation, and that sort of discipline instilled some appreciation. Then after that, I took advanced math for 3 years under a teacher named Art Smith, and he covered all the topics that one would, trigonometry, geometry, a little bit of calculus. So I was well prepared, and not only that, but found a great interest in math, but I was also well prepared for when I got to college.
Was math your favorite subject in high school? And were there any subjects that you hated?
Math was my favorite subject. My only thing I really didn't like was spelling. Of course, there was no course in spelling, but in English, you give a list of spelling words to learn, and you're supposed to 100 words, and you're supposed to get 95 of them. So I took that test and got close to a little over 95, I think, and I tried to take it again to get a higher score, but I got a worse score, so I had to take it a third time. So spelling was my least favorite.
Was there any course you hated in college?
Yes, German was my downfall. I I really struggled with that. Even had to repeat a semester. So when I took the second year, there was a book with scientific chapters on science, and one of the things that was supposed to be on the test was to translate a passage from that book. Well, I spent hours and hours until I knew sort of the translation by heart. So anyway, I got through the second year of German actually with B's, but it was a great struggle.
After high school, why did you decide to attend Carleton College?
Well, that's another for instance where chance events occurred. I knew that I should go to a small liberal arts co-ed college since I was very introverted, and I thought that would be best for me. And of course, my mother had gone to such a college, Swarthmore. So had nature taken its course, I probably would have gone there. But my father got transferred to Chicago, and so and my uncle had come over as he often did, and they said, "Well, maybe you should think about something something in the Midwest." And my uncle suggested Carleton College, so I sent away for the information, and although the distance between Carleton and Northfield, Minnesota, and Chicago is still quite a ways, I was attracted to it, and after a great struggle, and I had never actually had a visit to Carleton, but something about it appealed to me, and I decided to go there. So, sight unseen, I picked Carleton and went there, and had it was a great experience for me.
Can you describe your experience at Carleton?
Yes, a number of things come to mind. First thing, during my freshman year, I got acquainted with another student, Roger Kirchner, who was also very interested in math and a top-notch student. And we became best friends, really a lifetime friendship, which turned out to be important in several ways later on. When it got to the end of my sophomore year, I had to pick a major. Well, because of the courses I had taken, I had two options: one to be a chemistry major and one to be a math major. And I was a little bit concerned whether as a mathematician I could make a living. So I went to the head of the department and I asked him if I could make a living, and he said, yeah, he knew somebody who got the job, and basically said, yes, I could. And of course, math was my first love, so I signed up to be a math major. Oh, that summer after my sophomore year, I wanted to take a book home from the math library over the summer to read. And I picked out von Neumann Morgenstern's books on the theory of games and economic behavior. And I was really impressed by the way, starting from very scratch, they'd built up a model of games, and I thought that's what. Or that's kind of the way math should be carried out. You think if you carefully work out your model, hopefully reflecting as much as you can of the real world, and then work from there. So I was felt very enlightened by that book. Well, they had an arrangement where you could, your senior year, you could write don't want to call it a thesis or a paper, do something on that ilk. And if you succeeded in doing that, you would graduate with honors. Kind of an alternative was doing well on your final oral exam, and then you would graduate with distinction. Well, I thought graduating with honors and having written something would be better. So I did something involving graph theory and Arrow's paradox. Arrow's paradox says there is no giving preferences of voters. There is no fair way of coming to a group decision. And I analyzed and said, well, what if we have just three people, and we have and their preferences among three candidates was equally likely. What is the probability that there was a outcome agreeable to all the three people? Well, the math department, probably the chairman, Ken May, said, well, I should write that up and submit it to the Math Monthly. So I did that, and that became my first mathematical publication.
Did any of your college friends also pursue careers in math or computer science?
Yes. Just my friend Roger went to Harvard to get a PhD. There were two other very good math students in the class. One of them also went on to Harvard. The other one went on to medicine. But we had the number of math majors at that time was something like 11 or 12, and the others did not go for PhDs. I think some of them went into, math education.
Why did you choose Princeton for your graduate study?
Well, that was due to another chance event. The chairman of the department at Carleton, Ken May, knew John Kemeny, who was at Dartmouth, and he wrote a famous textbook and was instrumental in setting up the computer system at. He basically invented the language BASIC. But anyway, he came to visit Carleton, and he described the math department at Princeton in such glowing terms that persuaded me that that's where I ought to go.
Who is your PhD advisor at Princeton, and what was your thesis topic?
Well, my thesis advisor was Harold Kuhn, who did a very famous piece of work on in game theory on games with perfect recall. Now, at Princeton, of course, Princeton happened to be a place where game theory, the origin of game theory, from von Neumann and Morgenstern. Of course, von Neumann by that time had passed away, but Morgenstern was there in the economics department. And just in the Princeton bookstore, there are a number of proceedings on game theory, and I was interested, so I read all that stuff. So that made me want to study game theory for a thesis. So I asked Kuhn to be my advisor, and he agreed. But he did not suggest a topic. He said, well, you ought to do something that find out what you're good at and do that. And he gave me good advice on writing a thesis and what style to use in expressing theorems, and to include a lot of English in your statements rather than math. And he introduced me to game theorists as the other came through. Well, another chance event, Bob Aumann was visiting Princeton and something in connection with Morgenstern. He had an office there was a consulting firm called Mathematica, and they gave him an office. His office was there, so he was a little bit fuzzy on exactly how he was associated with Princeton. Anyway, he had some suggestions as to what to work on. So I picked one of the topics he suggested, which was 3-person cooperative games without side payments, and the objective being to find all of von Neumann Morgenstern solutions to those. So after he got me started, and he had made sure I understood the first paper that he had written, and I was able to improve one of his proofs, which satisfied him that I understood the material. So I went and worked on that problem, and after I had solved it, I told him, well, now I have the answer. And so he said, all right, well, explain it to me. So we set up a time at the university where there's a blackboard and things, and I started explaining it to him. Well, I had only a few pages of notes on this thing, but after discussing it already for an hour, I wasn't done. So we scheduled a second hour. Well, about the end of that hour, I discovered there's one case I hadn't covered. So when we met for the third hour, and I fixed that case, analyzed that case, and he was satisfied. So I think that was really the examination on my thesis, because although Kuhn was helpful, and particularly in some of the early chapters, and spotted a couple of spelling mistakes which had to be changed. And in those days, you made your copies with carbon paper. So certain words you have to erase. And I was making three carbon copies because I had to hand in 2 copies of the thesis. I wanted one for myself and wanted one for Bob Alman. So I had to make all those spelling changes. So I passed I passed the exam with the committee. Well, later on, I was when I was going over the thesis to write the paper on it, I discovered one page where the subscripts and superscripts were all missing. Because in those days, to make a subscript or a superscript, you had to go back and turn the roll on the typewriter up or down to make them. So I realized that maybe nobody had read that far into the thesis. Of course, now having been in academia, it doesn't surprise me because I certainly haven't checked every line of every thesis I've ever been presented with. So, so with luck, Alman there is to be a mentor. And of course, Alman later got the Nobel Prize in economics, so I can say I was mentored by a Nobel laureate.
How did you wind up going to General Electric? And what was your job title when you joined?
Okay, well, there's another case where chancy event altered the direction of my life. GE, the research lab, particularly under Dick Shuey, tried to get students to come and work over the summer with the hope that they would like it well enough so that when they got out, they would, come back. And so the GE recruiter went to Harvard. And my friend Roger was looking for a summer job. So he interviewed with them. And he said, by the way, you ought to hire Dick Stearns as well. So without having sought a summer job, I was invited up for an interview and accepted the job. Now, the way it worked is that the different members of the staff there would make proposals to say, well, you ought to work on, here's something you work on. And one of the proposals was by Hartmanis. Now, Hartmanis had written a paper called the State Assignment Problem number 1. And he said, well, look, this was involving finite state machines and partitions with a substitution property. And he said, well, I know you can have, in effect, the input partitioned in one way and the output partitioned in another way, and they fit together. So he said, look at this. So I did look at that, and I made different examples, and in order to learn more about the problem, and I came up with the idea of partition pairs, which essentially is the example he had given me was that. But I also came up with the idea that you could have a lattice called the MM lattice, which would describe the set of all these pairs. So you've gone beyond just describing the pairs themselves. So that became the paper known as State Assignment 2. Well, that was before I had started my thesis. So I at the end of the next year, and Shuey called me on the phone and said, when you come back for another summer?" And I said, "Well, I think I'll be out." So they offered me a permanent job. I went up there, and it was Memorial Day in 1961. I remember it was a very hot day. And I hadn't, I was still in the process of typing it up. So, I just got tired of typing, so I thought, well, let's go for this job. So I was typing up while I was there. Well, I didn't realize it, but I turned out to be a little concerned of the people having not actually finished the PhD, still having to write it up. But there was nothing in the job description that said, well, this is conditional on finishing your PhD. But anyway, I typed it up as planned, and I was able to, they had a fall graduation. I don't think they have that anymore, but I was able to get my thesis in time for still to graduate in 1961. So of course it was natural, having started on sequential machines, that we continued our work on that, and we had several papers on it, which I won't go into. But finally, we decided we'd put the material together in a book. So that was this book on the algebraic structure theory of sequential machines. Well, it didn't turn out to be very practical, but it was quite enjoyable and rigorous, and we got many people who had read it said, well, it was their first rigorous presentation of something having to do with this field. Anyway, it didn't went out of print fairly soon, but that's how I got there, and how we worked on sequential machines.
Did you interview with other places for a permanent job, and why did you decide to go to GE?
Well, first of all, I didn't think I wanted to go into academia. Somehow teaching was not, at least at that time, was not attractive. I did an interview at Bell Labs. They decided there was no place for me, even though I had two things under my belt: the state assignment work and the game theory work. Someone from Philco asked me to interview, which I did, but that was nothing of, I told them I wasn't interested. So that was the only job offer I had, and I was really interested in going there. So that's what I did.
After you worked in sequential machines, did you work with, which led to your Turing Award with yours, Hartmanis? How did you get started working on complexity?
Well, Uris had read Shannon's work on, the information theory, and he thought there must be a reason why things are hard, and maybe something like that might be the foundation for complexity. Well, and we thought that maybe trying to study the transition from finite state machines to context-free languages to Turing machine, maybe kind of studying that transition, maybe that would be helpful. And we had some preliminary stuff on Turing machines, not really complexity, and I've forgotten what it was. Yours is speculating that we had just rediscovered some things about recursive sets or something. I mean, I don't know exactly. We were thinking of complexity classes as the set of all things that you could do in a certain amount of time. In a sense, that's an easiness class, things that you can do in this time, but obviously we're not going to call our stuff computational easiness. Anyway, paper came out by Yamada on real-time countable functions. And that was really the missing piece, because basically he was talking about now what would be called, time constructible functions. And so somehow we had the idea of what a complexity class was, and now we saw that in effect a computer could, particularly a Turing machine, could keep track of time, like when 1n squared time, when 1 squared and 2 squared and 3 squared and 4, keep track of those time intervals. And so that's what we needed in order to do the diagonalization. So that was the final breakthrough. And at first we used his model. His model was to put out an infinite sequence. And so we developed a hierarchy based on infinite sequences. Well, there was also at that time the language recognition problem, where at that time there wasn't a standard even to work from. Well, we could show that the same thing applied to the language recognition problem. So that's how we put the thing together. Then, of course, we wanted to get that out to the computer science community, and many of the what we could call theoretical computer scientists attended a conference called Switching Circuit Theory and Logic Design. And so 1964, we presented our results to that group, and of course our published paper came out subsequent to that. So we also presented it at an IFEPS conference, which is another way of reaching people. And having aptly named it on the computational complexity of algorithms, it a catchy title, and people started working on it.
Can you elaborate any more on how you went about developing your results?
Well, I think I have kind of elaborated on it. I mean, the hierarchy theorem says that if we give you a little more time, and the one we worked out was saying, well, if you square the amount of time, then you can do something more that you can't do uh, in the given time. And that was to say that was all done with a diagonal proof using Yamada's idea of real time countable in order to switch simulations from simulating one Turing machine to simulating another Turing machine.
How did you hear about that? You hear about winning the Turing Award?
I was at home, and Dick Karp called and said, basically told me I had I won the award. Now, as you may recall, you had submitted the nomination the year before and been encouraged to repeat resubmit it. So it wasn't a total surprise. But he said the only condition was that I'd have to go to Phoenix and give a talk and to accept the award. And of course, I readily agreed to that. The one thing he didn't tell me was that the ACM wanted to make the press release before this became generally known. So, in addition to telling my family, trying to explain to them what this award was, I told the colleagues at the university and excuse me, the university put out their press release before the ACM did.
What was the impact of winning the award, and how did your family react?
Well, the family, the family was pleased. The award carried a monetary award of $25,000, which was a big improvement from earlier days, but now it's worth $1 million. So only one of the local TV stations picked up on the announcement and did anything about it. They sent somebody over to the university to take a brief picture of me, and they wanted me to sit at a terminal. So I sat at the terminal, and just what are you going to do? Terminal, so I sent a message to the faculty saying, well, they're here taking my picture. So anyway, that appeared on briefly at the end of the nightly news, and remember the announcer said, well, that's something to do with algorithms. So, well, I had done the work purely the pleasure of doing mathematics is a pleasure, and that's why I do it. Proving theorems is the ultimate rush for a mathematician. So I thought that would be satisfaction enough. But then once the ACM said, well, he's very smart, the other people thought, oh, he must be smart. So I was raised to the rank of distinguished professor at the university. I got an alumni award from Carleton as an outstanding alumni. Of course, luckily, my friend Roger Kirshner had gone back as Carleton as a teacher, so I just told them I'll nominate me, and he did that for me. So it continues. More and more people are, because the press, as time goes on and the prize amount goes, the more and more people hear about this. It turns out that, a lot of people know about the award. And my wife is quite happy to explain to people that I won the award, so I don't have to do that myself. Now there's now a called the Heidelberg Laureate Forum, where winners of the Turing Award and the top math prizes are invited to Germany every year and meet with students they call young researchers who have applied and been accepted to that program, and you go there and try and influence them, and they want to have their picture taken with you, and you feel like a rock star. Another related incident when last summer we went down to see the eclipse of the sun, and we took a plane to Charlotte, where we then went on to Clemson, and my daughter decided to go with us, and she had a different seat on the plane down there than we did. Well, she got talking to the woman next to her who was in computers, and they mentioned my name and computational complexity, and she was thrilled to have me on the plane and wanted to take a picture with me, and she said this was better than having Taylor Swift on the plane. So that was so they're just rewards. They're just rewards that come with the recognition that that I never thought of. Just a bonus on top of having actually done the work.
Can you tell us about your work with Fred Henne?
Sure. The hierarchy theorem that Hartmanis and I developed said that, well, if you, in order for us to prove that there's something that can be done at one time and not at another, that you would have to, if you squared the one function, then it would have more time. Well, that didn't really seem to be the best one could do. It would seem unlikely that things you could do in time n were the same as you could do in time n squared. And time n squared was the same as you could do in time n cubed. So I thought there ought to be something better. Well, in our proof, we simulated, you had to simulate Turing machines. And we were, and of course, the Turing machine we constructed to do things in the one time that you couldn't do in the other had to have a limited number of tapes. But it had to be prepared to do things that Turing machines with more tapes could do. So in order to do that, we were putting all the information onto a single tape from the machine we were simulating. And that led to an n squared, because with each move you would have to, there were two ways you could do it. one with each, after each step of the Turing machine you were simulating. You could readjust the take copies of the tapes on the one tape so that the places where the heads were lined up on the head square of the tape, the single tape. The other method is that you would mark the location on the tape where the head was. So after each move, you'd simply change the marker where the heads were. Well, of course, with many tapes, simulating many tapes, those markers would get farther and farther apart. So that's where they require n squared. The other method of moving the tapes, moving all the tapes, that was also n squared, because the amount of information on the tapes, each time you made a move, the amount of information you put on the tape might grow. So that was so we had two methods of doing the simulation. So I thought to myself, why not? Maybe there's something in between. So, and what's that mean? That means you readjust the tapes, but you don't readjust the whole tapes. You just take a portion of the information and shift that back into place. So I said, well, if we let's break the tape into zones of square size. One zone of 2 squared and 3 squared and 4 squared, and only go to clean up the information in one zone whenever necessary. So, cleaning up meant shifting a lot of information at once. So I had the idea of the second tape. So I could take a block of information and shift that on the tape. And so anyway, that worked out to be f to the 3/2 power over g would be enough to guarantee you could do more in f. So that was an improvement over n squared. So I thought, well, maybe we can do better than that. So I said, well, maybe we can have the zones be n cubed size and then break those up in n squared size, and we would use the n squared method to clear up the zones of cubic size. Anyway, that worked out to be not 3/2, but 4/3. And became apparent then that this generalization you could say in addition to that, have zones of the power to 5. And so we say, well, why not use as many zones as you can in the limit? So now the question is, what on earth does that mean time-wise? Well, Fred Haney had been hired by Dick Shuey for the summer, and he had an office next to mine, and he was clever at counting things. So I went into his office at really the end of the day, saying, look, I have no idea. Here's how I want to do it, but I have no idea how to, what the time this has taken. So he took that home with him at night, and he came back the next day and said, well, let's see, your method takes log n squared, and but here's how it should be done. So he had worked out that the zone should be exponential in size. And so that was he supplied that piece, and a very clever. I wouldn't know, something I never would have. Don't think I would have thought of. So he was able to finish off what I had started. So our work was really sequential. We never sat down together and said, let's solve this problem. But operating sequentially, we came up with the solution, which enabled the present form of the hierarchy theorem, which says that f log f over g was enough to give you more time. So that meant that in particular, something you can do in, say, n squared could be add a little bit, n squared, into the 2 plus epsilon, that's already enough to give you more. So every kind of smooth things out and made it into changed an ugly theorem into a pretty theorem.
You work on space complexity with Hartmanis, and Phil Lewis has been influential. How did that work come about?
Well, Phil Lewis was pretty insistent that we should look at space as well. I thought kind of feeling it was trivial, but then we came up with a important idea, and that is the idea is that we would put the input onto a separate tape from the work, and we would only count the space on the work tape. So after he decided not to count the space on the input tape, then all kinds of things opened up. Because, and particularly then you could talk about space which was less than n. Particularly you could talk about log n space, which is proven to be a very useful concept. One of the things we proved was that given log n squared space, one could decide whether a string belonged to a given context-free grammar. And the method we did that is that we, in a sense, try segments of the tape, which is roughly 1 to 2/3 the size of the input, and analyze that segment of the input, and then if that turned out to originate from a non-terminal, and analyze the rest of it. Anyway, that proof became very important because Savage picked up on that idea and used it to show that non-deterministic polynomial time space, that polynomial space, deterministic polynomial space and non-deterministic polynomial space were the same. We also did some stuff below log n and down to log n. The only strange thing about the classes below log n is that somehow you need the assistance of what's actually written on the tape in order to find in order to do your analysis.
You developed an algorithm to determine whether a deterministic pushdown machine recognizes a regular language. What led to that result?
Well, when we were doing our space complexity work, uh, I wanted to show that recognizing that a push-down machine, if it was non-regular, would have to count, and therefore log n space would be required. Proof went like this: if you do a certain thing, the push-down stack would get too much stuff on it that that would have to count. So, in a sense, it was a constructive proof. The proof was finally say, well, then if it's not regular, then this is this machine that has to count. So anyway, when I went to the IFIPS conference, Seymour Ginsburg was there and was asking us what we knew. And he said, well, do you know, can you test a deterministic pushdown machine to see if it's recognized in a regular set? And I instantly knew that this was an implication of that proof. So the test then is to run the construction of the proof, which gives you a finite automaton, which is a candidate for the finite step, which is a candidate for the finite automaton that recognizes the context-free language. So all you have to do then is test that candidate against that with the grammar. So the construction involves several levels of exponentiation, because you have to account because if epsilon moves, you have to worry about whether the information on the stack is going to go poof and disappear before you're forced to count it. And so it's got to, what you pushed on the stack has to have certain properties that it won't disappear poof. And anyway, it's described me as both the proof was difficult and that the time of the algorithm was remarkably large.
Let me change topic here. Can you please tell us about your first exposure to computing?
Yeah, so I never seen a computer until I got to General Electric, and there was no computer when I got there, but they soon got the time-sharing system. May even have tied into the time-sharing system at Dartmouth, where you that ran the basic program, and it was run on a teletype. So you'd type in your program on a teletype, and the output would show up on the roll. And it was, of course, a long time to teletype for to print something out. So you had the ability to just look at a portion of your program. So you say, well, show me lines 400 to 500, and would print that out, so you didn't have to look at your whole program. So that was my first experience. Soon they added Fortran to that time-sharing system, or GE added the Fortran. And there were certain problems where I had to use Fortran because I think it was because I wanted to write files on the disk. And the basic language didn't have that capacity. So for no other reason than then wanting to use the that capability, but I have to write a Fortran program. Then later, the Algol compiler was developed by Dan, Phil, and some programming help, and that was put on the system, and I switched over to programming in Algol. And I would write program. Probably the most interesting use I made of the computer was a certain game theory problem when I was interested in questions regarding what they call the kernel of the game. And when one would have to test a certain vector of payoffs to see if it was in the kernel. And that was, you could easily make a mistake doing that by hand. And so I wrote a program which I would then experiment and put the description of the game in there, and I would experiment with different vectors to see if they were in the kernel. Well, then there was the question of whether if the vector you were testing was not in the kernel, could you do something to make it, or make it in the kernel, or get it closer to the kernel? And so, well, that was easy to do. I put in the loop where I put in the vector and to figure out it wasn't in the kernel, and figure out the biggest change I could make in the vector, which would make it closer to the kernel. And so that led to a game theory paper I wrote on convergent transfer schemes. And I found from time to time the computer is a useful tool for working out examples and or as a computer aid in research.
When did you first think of yourself as a computer scientist, and how did that come about?
Well, at the time, there was nothing, when I came to GE, there was nothing called a computer scientist. And I took on the title mathematician. They asked me what title I wanted. That was the title I wanted, mathematician. Well, it turned out, that the work, the group of people who were interested in the work were what would now call theoretical computer scientists, although the people would think of themselves as electrical engineers or mathematicians. And there was just discussion around whether there was such a thing as computer science. If you went to academia, would you dare be in a department called computer science, or would you want a joint appointment with some other department? Well, then, computer science departments started showing up more and more. Eurus Carmanis, of course, went to Cornell early to start a computer science department there. So I started thinking myself as a mathematician / computer scientist. At some point, I joined the ACM, so Association for Computing Machinery. So that is a indication of starting to think as a computer scientist. Later, I dropped my memberships in the math societies And so I guess that completed the transition, although still think of myself as a mathematician slash computer scientist. So all I really do is prove theorems.
How did you get involved in parsing syntax-directed translations and attributed translations?
Well, uh, context-free languages was a hot topic at that time. And General Electric was getting into the time-sharing business and learning languages. One would have to learn syntax. And there were some interesting papers around and about parsing. And several kinds of parsing had been invented. The one being the LR of K parsing that Knuth had developed. And we thought it made us think about parsing. And naturally, when you parse, you have to do something. If you're really running a compiler, you have to do something in addition to just recognizing that the thing has been correctly written. And so you want to take actions while you're parsing. Well, then, if you're taking actions while you're parsing, you'd like to take those actions as early. The earlier you can take an action, the better. So we came up with a concept we called TD languages for top-down. When we submitted that paper to Knuth as editor of something, he said, "You ought to call that LL parsing." Since he was the editor, that's what it's been known ever since. Well, then, first, the syntax-directed translations was really about taking actions to make outputs. And a compiler takes actions, of course, to all kinds of actions as part of the compiling process. The idea of attributes was already around. Knuth had a paper on attributes, but we saw that we asked the question, how are we going to pass those attributes? How are we going to actually do the computation of these attributes while the parsing is going on? So that led to our paper on attributed translations.
The textbook on compiler design, written by the two of us and Phil Lewis, was an early book on compilers. Can you tell us what led to this book?
Well, we basically we had a lot of we had developed the theory as discussed, and the development of the Algol compiler. I don't remember that preceded the book. Anyway, you know a lot, and you want to write a book. This is the book here. We intended it as a textbook, so we found that if we put it in the IBM series, that they were willing to sell the book less than if it was sold as an academic book. So that's why we published it in this particular series. Well, it took a long time to write certainly took several years to write the book, because I don't know if it was a little bit painful to write a book or because we were distracted by other things.
How did you get involved in Fortran compiler, and what was that experience like?
Okay, well, at that time, GE was getting into not just time sharing computing, but they were planning to manufacture and sell computers, and for some reason they wanted a new Fortran compiler for their computer, and so the main work was going to be done in Phoenix with their computing division, but we agreed that we would write a front end for the compiler. So the people in Phoenix said we want such and such for the next pass of the compiler. So we put our theory to the test and to write the front end because we did like to support the company when we could. They sent somebody from Phoenix to work on the front end as I designed it, and turned out that was the coldest winter ever remember in Schenectady with piles and piles of snow. But anyway, we did it. There was some hardships in doing it. That according to the Fortran, the spaces don't count, so you have to look way ahead to know what kind of statement you're working on. They wanted they also wanted to be able, when you wrote a Boolean expression, they wanted to be able to rearrange the terms to what they thought would be better. And the third peculiar thing was with there's certain called inline functions in Fortran where you make a single statement to define a function. And they wanted those to be treated like macros. So there were a number of problems there which weren't strictly parsing, but we got through it. And but in the meantime, General Electric sold their computing business to Honeywell. So by the time the project was finished, it was a Honeywell project. And because Honeywell, since no longer making computers, I don't know what happened to that, whatever happened to that compiler, but there were certain strange things built into it that, for example, because the built-in functions were being treated like macros, I found a way to almost almost to call them recursively. Not quite, but they would call themselves to a limited depth, so one could test. If one ever found the Fortran compiler, one could test it on that example to see if it behaved that way. Another thing we did was that complex numbers were written in left parentheses, comma, right parentheses, and we had it so that you could actually put expressions in for. The design only called for putting constants in for the complex numbers, but we could we treated the construction of a complex number as an operation. So whenever it finds a compiler and wonders about it, one can try writing a complex number with using variables instead of constants and see if it goes through.
At GE, the two of us, together with Phil Lewis, worked on the traveling salesperson problem. Can you tell us how that work started?
Well, I guess there are two things. One is that some components of GE had problems, which were traveling either correctly modeled by traveling salesman problem, not actually sending salesmen around. For example, there was a problem of drilling holes in a sheet of metal, and the quicker you could get from one hole to the next, the better you were. And there were several colleagues at the research lab who had sorting algorithms, not sorting, traveling salesmen, algorithms for traveling salesmen, including nearest neighbor and some of the others, and we decided it would be fun to analyze them. So we did a paper on analyzing the traveling salesman problem. Originally we were calling it traveling salesperson problem, but the referee found that objectionable. So reverted to traveling salesman problem.
At GE, the two of us also worked with Phil Lewis on concurrency control in database systems. Please tell us what led to your interest in this topic.
Well, databases, concurrency control, databases was of interest to the company. One particular database need they had was in regards to their atomic energy program, because they're required to keep track of strict government regulations on keeping track of where the nuclear fuels are. So they were very interested in a robust concurrency control. And our main paper on that was to show that to be consistent, if the program was, if the database program was both reading and writing, then they would have to be serializable. And there was an interesting exception for programs which didn't write. And we did some, I think we also had some other ideas in some conference proceedings. Phil Lewis pursued that much further. Eventually wrote a book on concurrency control, whereas we moved on to other things.
Along with your work in CS, you were continuing to make contributions to game theory. Can you tell us about this?
Yes. Of course, my thesis work on three-person cooperative games without side payments. There's an interesting side story on that. When I came to GE, that's exactly what they had done. They had colluded with two other companies, Alice Chalmers and Westinghouse, as far as bidding on contracts was concerned. So sometimes one company would make a lower bid, and sometimes the other companies would make a lower bid. So that was cooperation, and there were no side payments. I think they actually used the phase of the moon as a random device to decide who was doing what. So it was kind of a joke that they hired me at just that time. Well, anyway, beyond the thesis, the next thing I did was, my thesis was on von Neumann Morgenstern solutions. And there was always a question of whether a von Neumann Morgenstern solution would always exist. And I found an example for without side payments, where there was no von Neumann Morgenstern solution. Of course, the original question was for what about games with side payments? And the solution concept was already in trouble because there were games where the solutions were too abundant, and where any kind of a compact set could be part of a solution. So it was in some sense already on the way out. People were looking for alternatives, but that was a start of the downfall, and it was finished off by William Lucas, who took the same ideas and found a game with side payments that had no solution. So after that, I did my work on convergent transfer schemes, which I already discussed. Then some computer scientists were doing some work, consulting work for the Arms Control and Disarmament Agency. The main contractor was the Mathematica, and the consulting firm in Princeton. And they would gather some computer scientists, some game theorists together for a couple of weeks, and just to work on their problems. And one of the problems that Bob Alman and Mike Mashler had worked on was on repeated games of imperfect information. And they had shown that, yes, there was, they knew how to solve the games if one of the players had had the perfect information about the other player. But so they knew when they had strategies for the player with knowing whose basic type was the secret and the one who didn't. But the question when I joined this group, which was not the first meeting, was what about what do you do if both players have imperfect information about the other player? And anyway, that was still open at the end of that particular session. And so I took that back to GE with me to think about it. And again, I'm thinking about the problem top down, and thinking, how would you show there's no solution? Well, I had the idea that since the game was repeated forever, sort of the first, the first 100 times or so forth wouldn't count. I mean, whatever payoff you got then was, since you were interested in what happened in the limit, you make it all up. The beginning didn't count. So I thought, well, one player should wait until he gets all the information about the other player, and then make his the thing is if the one player may have a different, maybe one of several types, and the idea is you can make moves to conceal your type, which means doing the same thing regardless of which type you are, or you can make moves that are more favorable to the type you happen to be. Well, as you make the moves more favorable to the type you have to be, the other player can start figuring out which type you are and play accordingly. So anyway, my idea is that it's sort of like picking the larger number. Say, what is the strategy for picking the largest? You and I are each supposed to pick a number and see who has a larger number. Well, there is no optimal strategy because obviously if I know what probabilities you're using on different numbers, I'll just pick a number much larger than what you're picking and vice versa. So not all games have solutions. So then if I was going to wait out the information, then how could somehow I'd have to measure the information. So I wasn't sure how to do that. So I went to Phil Lewis and into his office and said, well, I want something like, I told him vaguely what I wanted, and he made a suggestion, and that suggestion worked. But somehow I never given him credit for that. He deserves credit for providing me with that idea. So anyway, I was able then to follow through on that idea. One player waiting out, now having him could measure the information for the other player and understood what it meant to get all the information that player was going to provide. And anyway, it showed that there was no solution for that case. Well, still, that went into a report to the Arms Control Disarmament Agency, where very few people knew about it. The proceedings were passed around among a few people, but it's not generally known. So then, at some point much later, in fact, I think it was around 1985, Alman and Mashler decided to take that information and put it together and into a book. And so they invited me to provide a chapter, basically what I'd written for the Arms Control Disarmament Agency, make that a chapter in the book. But that wasn't a big enough contribution to be made, be considered an author. But it was, here's the book here, and you read the fine print. It says, with the collaboration of Richard E. Stearns. I don't have my glasses on, so I think that's what the fine print says. So it's kind of a semi-author. But anyway, this book did win the Lancaster Prize for Book of the Year. So that's the story of how I almost won the Lancaster Prize. So anyway, continuing with my contributions to game theory, there were some game theorists were proposing that to measure a strategy in a repeated game, they're asking, supposing an automaton is playing that, is moving the strategy, and let's call the number of states that automaton uses as the measure of the difficulty or complexity of the strategy. Well, in my view, that was not really a good measure, because you can there are very simple ways to describe some non-regular sets. For example, if you wanted to, if you took the strategy that after every thousandth move, you'd go left instead of right. Well, that's a very easy strategy to describe, and to write a simple little program to do it. Namely, you count up to 1,000 and repeat. But that would take a 1,000-state machine. So I thought, as a alternative, that one should say, all right, we'll take instead of a finite state machine, we'll use an automaton with a bound on the amount of tape. So it'd be like a linear bounded automaton, but with no input, so not exactly linear bounded, but so anyway, that the measurement by the amount of space you needed to carry out the strategy was you could carry out a very complicated strategy and a very limited amount of space. So, but the difficulty with that, which is, of course, as obvious, is that the algorithm might be exponential in the size of the amount of tape you're using. So, but that measurement actually resembled the Kolmogorov complexity of single sequences, in that you could, if you change the tape alphabet or did things like that, the measure is independent of the. I mean, you could write the strategy down on the tape, and the complexity was basically independent of the number of symbols you were using, or in the same way that Kolmogorov complexity is invariant and in respect to the language you use to describe it. So let's see that contribution, and that I gave that talk out in Stanford, and I had it written down, and that became a Stanford report, even though I was out there for 1 week, and I had presented that result at a game theory conference, but never came out as a publication. And I've also recently been writing a paper on games with imperfect recall and showing that something, essentially showing that if you have a little bit of imperfection, there's still good strategies for it. So it's not a big cliff when you go from perfect recall to imperfect recall, but it's only as the amount of imperfection, so to speak, grows that the difficulty in describing strategies grows.
What influenced your move from GE to the University of Albany?
Well, the first thing was that the culture at GE was changing. When I first got there, all the money came from, in fact, taxing the components of the company, and then they would say, go do something interesting. But more and more, they were asking you to find components of the company that could support your work, or asking you to get government contracts. So the freedom was slowly being whittled away. And I think that happened not only at GE, but on research labs around the country. Okay, second of all, I thought, now that I've done all this work, I have something I can contribute to teaching. So the prospect of teaching now became more interesting. Also, I did teach a database course at RPI for a semester to kind of verify that I could teach and have some feeling as to what teaching would be like.
Was it compilers or databases? You taught at RPI?
No, it was databases.
Okay.
I also taught compilers sometime earlier at Union College. So then the university offered me a very attractive position as a leading professor with a salary which was essentially the same as what I was getting at GE. And I wouldn't have to grovel my way up the academic ladder from assistant and associate, that route. And it was easy to switch to the university because that was an easy commute from where I was living. And of course, Dan, you were there, which was, attractive. It looked like the department there was up and coming. And so for all those reasons, I switched.
At UAlbany, your work with Harry Hunt introduced the notion of power indices for hard problems. This was a precursor to subsequent work by other researchers and notions such as the exponential time hypothesis. Can you tell us how the work on power indices came about?
Well, in general, Harry Hunt's research, three things that are very important to him. One is to prove things with using few assumptions as possible, so it has the widest possible applicability. The second is to make your reductions as efficient as possible, that is, as small a size as you can, so that the implications for hardness are stronger. And third, try to make your reductions go into natural subsets that might occur in practice. So you're really proving something hard. And its work was kind of in line with that philosophy. We defined the power index of a function. For example, 2 to the n was called power index 1, and 2 to the square root of n, which is called power index 1/2, and so forth. Then we noted that if you assume that the power index of Saturn is 1, which we call the satisfiability hypothesis, then according to the size of the reduction you made, you could make conclusions about the complexity of the thing you were targeting. For example, the partition problem. The reduction from SAT to the partition problem, as even originated by Karp, is n squared in size. That is, given the SAT problem, it maps it onto a partition problem, which is n squared. So that means there's a match between the size of the reduction and its implication for hardness, and the algorithm that we have. I mean, there's no wiggle room there unless you can do SAT bigger. And the suggestion we made is that if the conclusion you draw from your reduction doesn't match the best algorithm you know, then there's room for improvement. Either improving your look for a faster algorithm, or look for a better reduction. So those are the two ideas of using that notion. One, to talk about the implications of your reductions according to size, and the other to suggest where you should look for improvements either in the algorithm or the reduction.
At UAlbany, you also worked with Harry Hunt on algorithms for combinatorial problems by exploiting subproblem independence. Can you describe how this work came about?
Well, again, looking for cases and situations where where the structure of the problem gives you improvements over the general algorithm. And we looked at satisfiability, and we looked at it as an algebraic problem. That is, you want to evaluate the sum of products over a ring, and the conditions that would make it go through, that is, which would make dynamic programming go through, or the distributive and commutative laws. So, and we called it channel width because that is the amount of information you need to pass from one sub-problem to another. Now, this is also, these same ideas can be attributed to tree width, but our thinking was that these things were more naturally described as sum of product problems. There's a tree width people published tree width problems in tree width by saying, oh, well, for bounded tree width, this is polynomial, which is actually a consequence of the idea that the problem can be solved by non-serial dynamic programming. But of course, if you say this problem can be solved by non-serial dynamic programming, that's not as sexy as it's polynomial for bounded. So we perhaps we could have gotten more notice by presenting it that way. But anyway, this algebraic approach did lead to a couple of other papers. One is we showed how this could be extended to quantified formulas. And the second, we showed how if you have something that can be done non-deterministically in the sublinear space and in linear time, that that can be explained entirely in terms of channel width. That is, all those problems could be reformulated as SAT problems with limited channel width.
You also worked at other problems with Harry Hunt, such as the complexity of simple Boolean formulas and using algebra to characterize the complexity of problems. Can you tell us about this work?
Well, again, that fits into Harry's basic philosophy of making sure that your reductions go to natural subsets. So, in the case of the Boolean formulas, it considered equality of two Boolean formulas and containment. And the results were the form, well, this is the difficulty is hard, even if only the variables only appear once, on each side, and one side is a CNF, and the other side is a DNF of two levels, a CNF of DNFs. So the idea that these are the very simple formulas, ones that are more likely to occur in practice, and the other work, again in the trying to achieve the most generality for results. So they all kind of fit in that rubric. And I should add that during the time I was chairman, this was very helpful to me to work with Hunt, and otherwise I might have stagnated.
Can you talk briefly about your PhD students at UAlbany and the nature of your interactions with them?
Yes, there were a couple of students that come to mind, which I worked with Harry Hunt in advising. One was Venkatesh, or Venki for short, and he did things like investigating planar problems and why they might be easier, and how tree width would apply to those. The other student I worked with Harry on was Madhav Marathi, who was interested in, among other things, the complexity of hierarchically presented problems. And the nature of the interactions. Harry did a lot of the interacting with these students, and I was mainly following his lead. And there were other PhD students at the time, which I served on their PhD committees and who worked with other combinations of faculty members. I know you and Harry had several students. Then there was Tom O'Connell, much later, who was interested in game theory. And he worked on some implications of limited information. And mechanisms design, showing that even under very simple conditions, mechanism design led to some very hard problems.
Can you tell us about the courses you taught at UAlbany?
Let's see, I taught the theory course many times, both to graduates and undergraduates. I did teach discrete structures once or twice before it got so big. I taught databases and algorithms. And I also taught the introduction to computer science for non-majors, and that was a giant course. And I figured I should contribute along with other faculty members in teaching something large. The advantage of that course was that it was taught in the language BASIC, which was a language I knew, so I didn't have to learn the latest version of in the Algol, C, Pascal, that sequence.
For some time now, you've been working on the topic of discrete graphical dynamical systems. Can you discuss this work?
Yes, this is a project that our former student Madhav Marathi has been leading, getting financial support for, and I was invited to join as sort of a subcontractor on this work. Then it leads to some challenging problems, like what are the consequences of these the nodes in this network that they have certain kind of functions. What are the implications of those functions, and what happens is in the course of operations as as these networks proceed from one time to another. What are what can you say about the overall flow of information and the changes to the configurations?
What other problems have you been working on since you retired from UAlbany in 2000?
Well, I mentioned that I was currently working on writing a paper on games games with imperfect recall, which involves. I've always been kind of interested in how information relates to game theory, and there's a difficulty in dealing with these things, in that the set the information as value. Two pieces, you might say two pieces of information which are very similar, are not so. The distinction is not important. So having to, I finally sort of figured out how to handle this problem where strategies have to be correlated, and you'd like to have less how much, I guess it's not a way of putting it, how much correlation do you need for a particular game in order to have an optimal strategy.
You published a paper with your father. Can you tell us how this came about?
Yes, my father was an expert on color. He worked for American Animated in the branch that produced dyes, and in particular the problem of matching colors. That is, if I take a swatch of paint to the store and say match this, how is that done? And in fact, he wrote a book on that subject, and he also actually did write a system for an early system to do this for the Benjamin Moore, the paint company. So, but there's a certain need for interpolation and extrapolation in the calculations. That is, when I take the swatch to the store to match the color, they sample it at maybe take 20 samples at different wavelengths. Well, the method of the standard method, maybe the supposedly accurate method, would require that you have a lot more measurements. And so you have to take these measurements from the measurement you've taken, and you have to extrapolate what that function looks like. And by the function, I mean really the spectrum of the color sample that you're looking at. And so we had discussions on how to do that interpolation and that extrapolation, and it's not very deep mathematics, but it's quite useful.
What's your opinion about the P versus NP question?
They are definitely different. I guess the question is, when will we ever get a proof that they are different? I wonder if we ever will get a proof. I mean, if I give you a Turing machine, for example, and say this is solving satisfiability, how would you know? I mean, if you want to show that no such machine exists in polynomial time, I say, well, supposing you do have a machine. Well, what can you ever say about such a machine? I mean, the Turing machines are really inscrutable. So try to say anything about what an arbitrary machine is doing is it's basically undecidable, and of course, depending on how you phrase the question. And the problem really gets back to Turing machines. That is, you have a non-deterministic Turing machine, and you want to make a Turing machine which does the same thing. That means, to some degree, the Turing machine has to anticipate, what the non-deterministic. Somehow, it has to condense the operations of the non-deterministic machine to some degree, and I don't know how that. I don't see that being done. So it's a very hard problem, and may never be solved.
Can you tell us about the theory conferences of the 60s evolved into Fox and Stock in later years? And more generally, how did conferences come to play such a large role in the culture of computer science?
Well, at the outset in the early 60s, the people who were doing theoretical computer science was a small community. Now, I mean, you can argue a little bit about what should be in, what is theory, and you can you can point to people say, well, these people doing AI, they weren't part of the conference and so forth. But that was the conference was really which was then called switching circuit theory, and logical design was the place where people interested in theory got together and exchanged ideas, and that time the proceedings were being put out were really almost full papers. The program committee would select the papers, and maybe half would get in or something. I don't remember the statistics. But and once the proceedings got out, that was practically a publication, in the sense that most people who were interested had access to it. For example, Cook's paper was never published outside the conference proceedings. Well, as time went on, these things got bigger and bigger, and more topics came. There were more papers on the same topic. Well, for example, languages. There are more and more papers on languages, more than certainly a lot more than could possibly be accepted. And so the special interest group POPL was spun off of that, and the database has got. When they grew, that was also spawned off. Well, I should say, besides the switching in theory and automata theory, switching circuit theory and logical design, which changed names a couple of times until it became Fox, the Foundations of Computer Science. A second conference was started, so there'd be a conference in the fall and one in the spring, the other one being a stock. And one was sponsored by the ACM and the other by the IEEE, the Engineering Society, or to accommodate papers. So those two conferences are really the spawning ground for a lot of spin-offs from that. So in some sense, the development of computer science can be measured by the growth in these conferences and the spin-offs they produced.
What are your views on the development of computer science?
Well, first I have a theory that somehow things are driven by the hardware available. So when I first started out at GE, we were working on a teletype, and after a while we had little terminals which would display characters, and but with developing more and more computing, more sophisticated terminals, then something like Windows became possible. I mean, suddenly there was enough computational power to do some very sophisticated graphics, and I think now there are things in artificial intelligence which seem to be things that are computational heavy, and now can be done. So, in some sense, we're being driven by the hardware, and of course, it's obvious larger and larger problems are being handled, and less and these are not as amenable to theoretical analysis as some of the other things. I mean, they have programs to learn to play games, and no one really the programs learn, and no one really understands what they've learned, only that they're playing well. So I don't have a grand vision as to what happens. I mean, there are developments that really amaze me, like when I Google something, things that instantly, how often it comes up with relevant papers and references.
Do you have any advice for young computer scientists?
Well, the first piece of advice is to do what you love. When I was at the Heidelberg conference, there was a young researcher going around asking people to, you had something like an autograph book, and saying, write down, not only do I want your signature, and I want your advice. Say something. So I said, do what you like, do what you love or something. And she said, well, that's what everybody's saying. And so sure enough, some of the, I asked her, show me what some of the others wrote, and they wrote some of that. Second thing is picking the right model. And the third thing is to think top down. Now, earlier in this interview, I mentioned the work with Henny, and how I started thinking, well, how can I take these two ideas, these two approaches we have, and and merge them, and gradually that idea was refined. You should do what you love. Be sure to work on the model to get the right model, and think top down.
Looking back, what turning points and major decisions affected your life?
Well, I mentioned things as we kind of went along here that things just happened to me, kind of without too much planning. The suddenly thinking about Carleton, having the visit to Chamonix, which persuaded me to go to Princeton. My friend Roger suggesting to GE that they hired me and things like that. So I don't only real decision I made, I guess, was to switch from GE to SUNY.
What have been your interests outside computer science?
Several we could talk about. First is in dancing. When I started at graduate school, there was a folk dance group, very active one, and I tried that out and found it good exercises, stimulating and sociable. So, and I continued, when I got to Schenectady, I continued folk dancing with a group there. After dancing there a year, a young woman caught my eye, came, and after a year's courtship, I married her. And became my wife, Charlotte, of course. And we married in '63, and so that's 54 years we've been married. So that was a very happy occurrence. As the the folk dance group kind of faded, we started doing contra dancing as well, and finally mainly contra dancing. And after that, we got interested in English country dancing, which I don't know if you've watched a film, a Jane Austen film like Pride and Prejudice. You'd see that kind of dancing there. And now that I've slowed down a bit, I can't make moves as fast. The contra dancing is now out, but I can still do the English dancing because it's slower and emphasis on on grace and being in tune with the music rather than stomping around. And we've gone back to some international folk dancing. So that's been a lifetime hobby and joy. Another activity when I was young and like in high school and even before that, I got very interested in chess. My father took me down to a chess club when I was in 7th grade, and I played in that chess club I was the only kid in the club, but I did that for 6 years and became somewhat proficient. And so I did far less of that when I got to Carleton, and even less, hardly at all, very little since then. In the meantime, I'd been playing bridge at home, and at Princeton I started playing in a bridge club there, and I've been playing bridge fairly regularly since then for a number of years. We were just in a small group of couples who got together, and then since then I've started playing in club games as well, gone to some of the national tournaments, and achieved the rank of Silver Life Master, where if you know the scheme of things, it's not really very far up on the different ranks. Then in the early 70s, when McGovern was running for president, I got kind of interested in politics and sort of figuring I should do something. And I was invited to join the Democratic Committee, which I did, and got involved in some political infighting there, and became chairman of the party. And I was party chairman in Niskayuna for first for 4 years, and then later for another stint of a little longer. So I've always felt it important that you ought to you want to do something for society's benefit, you ought to work on that. Let's see, then, I guess one final thing. When my son was in the Scouts, and the Scout leader wanted to run a Pinewood Derby. Pinewood Derby is when you make cars and they go run down a track by gravity, and try to pick a winner. And the Scoutmaster, Mark Borum, asked me, well, how should we do this? I developed some schedules with the idea that instead of playing a knockout or something, that all the cars should race the same number of races. And so we had a schedule for that, and Mark Borum then wrote up the whole thing as an article in a scouting magazine. And so since then, that's become known as the Stearns-Borum method of doing car races. And if you Google Stearns and Pinewood Derby, you'll find there's another community which seems to appreciate some things I've done.
Okay, Dick, thank you. I think that's the end of the questions I planned on asking. Anything else you want to say?
Well, I want to thank you, Dan, for agreeing to be the questioner on this, and for all the good times we had at the research laboratory and working together at SUNY. It's been a great run we have had together, and very much appreciate that.
Thank you, Dick.